Gresham College presents 19th Century Mathematical Physics, James Clerk Maxwell, by Professor Raymond Flood.
So James Clerk Maxwell was one of the most important mathematical physicists of all time, coming only after Newton and Einstein. Within a relatively short lifetime, he made enormous contributions to science. Foremost amongst these was the formulation of the theory of electromagnetism, with light, electricity and magnetism all shown to be manifestations of the electromagnetic field. He also made major contributions to the theory of colour vision and optics, the kinetic theory of gases and thermodynamics, and the understanding of the dynamics and stability of Saturn's rings. His work on electricity and magnetism was such that Einstein enthused. Since Maxwell's time, physical reality has been thought of as represented by continuous fields and not capable of any mechanical interpretation. This change in the conception of reality is the most profound and the most fruitful that physics has experienced since the time of Newton. And I will come back and comment on that quote at the end of the lecture. While the distinguished physicist Richard Feynman predicted, from a long view of the history of mankind, seen from, say, 10,000 years from now, there can be little doubt that the most significant event in the 19th century would be judged as Maxwell's discovery of the laws of electrodynamics. Praise indeed. I will start by giving an overview of his life, and then we'll consider his major areas of interest and his achievements. And Mark and Julia, our lectures were carefully coordinated in order that they took all the good bits. Thank you, Mark. Thank you, Julia. Quick revision while you were talking. He was born the 13th of June 1831 in Edinburgh and moved in 1833 to Glenlair, an estate that his father had inherited and which is about 90 miles southwest of Edinburgh. He came from a financially well-off and well-established family. His father John had trained as a lawyer, but seems to have been more interested in what we might now call design and technology. His mother Frances was 40 when James was born in 1831 and died in September 1839 when James was 8. She died of stomach cancer. James, like his mother, was to die also of stomach cancer. From all accounts, James was a much-loved, precocious, curious and intelligent child, just like any grandchild. After his mother's death, James's father John appointed a tutor for him, which was not a success, to put it mildly. And as a result, James was sent to Edinburgh Academy and to live with relatives. This was just 2 years after his mother's death. P.G. Tate was another pupil at the Academy. And they became lifelong friends, even though as adults they competed for the same job on more than one occasion. It was while at Edinburgh Academy that he published his first academic paper at the age of 14. It arose out of his attempts to generalize the well-known process of how to draw an ellipse. If you have 2 pins in a board and a string attached to them, and you then push a pencil against the string to make the string taut and move the pencil, you will obtain an ellipse. James investigated what happens when the string is folded back on itself towards each pin. Here, from his collected works, is the opening page of the paper in the Proceedings of the Royal Society of Edinburgh. I'll give you a close-up in a moment. The title was On the Description of Oval Curves and Those Having a Plurality of Foci, with remarks by Professor Forbes. And let me go to the detail down the page. In the bottom left picture, the string starts at the left pin. And I was going to actually use this to show it, but as Mark said earlier on, when you do this, my hand is quite steady. I'm quite sort of pleased. But as I read it out, on the left-hand picture, The string starts at the left pin, goes round the pencil, and then round the right pin, and back again to the pencil where it is attached. So the length of the string is the sum of the distance to the left pin plus twice the distance to the right. In the bottom right picture, the string starts attached to the pencil, goes round the right pin, back to the pencil, then round the left pin, back to the pencil, and is then attached to the right pin. So the length of the string in this case is the sum of the twice the distance to the left plus 3 times the distance to the right. And the slide shows some of the ovals that can be generated. Here in this particular case, when the ratio is 2 to 1, in this case the ratio is 3 to 2. In the left-hand side, you get these oval shapes depending upon what length you take for your string. And of course, why stop with just 2 pins, which refers back to the title. And although Descartes had described ways of generating these curves, Maxwell's method was new. Maxwell's father John showed the work to a friend, J.D. Forbes, who was professor of natural philosophy at Edinburgh University, and who arranged for its publication. The reason I mention it now is that apart from showing his talent at such an early age, it shows of 2 lifelong characteristics that I'll come back to again and again: the ability to generalize and his ability and enthusiasm in geometrical reasoning. In 1847, James enrolled at Edinburgh University, where he would study mathematics under Philip Kelland, natural philosophy under James Forbes, and logic under Sir William Hamilton. And I'm pleased to note that Sir William Hamilton has not been mentioned until now. He was 16 and undecided on his future career and whether he should follow his father's wishes and become a lawyer. When he left Edinburgh University 3 years later, he was decided on a scientific career, or as he put it, I think most charmingly, to pursue another kind of laws. I want to pick out one investigation that he undertook at Edinburgh University, because it illustrates how he was a gifted experimentalist as well as a theoretician. He was like Newton in this regard. This excellent work was on the equilibrium of elastic solids and was published in 1850, and it will also come back into our story when I talk about electromagnetism. On the equilibrium of elastic solids. In it, he axiomatized the equations of elasticity and applied the results to a number of problems. He wrote, "There are few parts of mechanics in which theory has differed more from experiment than in the theory of elastic solids." And as I say, I'm picking it out, particularly because of the axiomatic approach that he takes. I have therefore substituted for the assumption of Navier the following axioms as the result of experiments, and then gives a couple of axioms. The equations deduced from these axioms contain 2 coefficients and differ from those of Navier only in not assuming any invariable ratio between the cubical and linear elasticity. They are the same as those obtained by Professor Stokes, I think that Mark was talking about, from his equations of fluid motion, and they agree with all the laws of elasticity. It was a very professional piece of work on a topic of current interest to many and brought him to wide attention. The picture is of Maxwell, aged 24. He went up to Cambridge in 1850 to Peterhouse College for his first term and then migrated to Trinity College, possibly because there might be better career opportunities at Trinity. He graduated as second wrangler, with E.J. Routh taking the top spot of senior wrangler, that is, obtaining the top first-class honours. In the subsequent competition for the Smith's Prize, Maxwell and Routh were declared joint winners. In the Smith's examination of 1854, Stokes' theorem, connecting surface and line integrals, was question 8. And Maxwell later made great use of this theorem in his work on electromagnetism. Maxwell had not done well. Not as well perhaps as Tate, who 2 years earlier had been senior wrangler and Smith's prizeman. I don't know if he had an aunt who reacted in quite the same vitriolic way, but then Tate wasn't up against Royth. All of them had studied under the great private tutor William Hopkins, as had Stokes, Cayley and William Thomson. In 1855 he became a Fellow of Trinity. This year also saw him publish the paper Experiments in Colour as Perceived by the Eye, as well as the first part of his paper on Faraday's lines of force, which showed the first evidence of his true genius. In 1856, Maxwell received a letter from Forbes telling him that the chair of natural philosophy at Marischal College, Aberdeen, was vacant and suggesting that he apply. He was young, 24 for a professorship, and relatively inexperienced, but others had been appointed at similar ages, as you've heard. William Thomson to his chair at Glasgow at age 22, and P.J. Tate to his professorship of mathematics at Queen's College, Belfast at age 23. Opportunities did not come up very often, and Aberdeen would also allow him to be closer to his father. However, his father died around Easter 1856 before Maxwell heard that he had been appointed to Marischal College, one of the two university-level colleges in Aberdeen at the time. The university year ran from November until April, when the students returned home to help with their parents' farms or trades or professions. So Maxwell was able to spend half the academic year at Aberdeen and the rest at his estate Glenlair. In 1858, he married Catherine Mary Dewar, daughter of the principal of Marischal College. Catherine helped him in his scientific experiments, both in Aberdeen on his colour experiments and later in London on kinetic theory, particularly on the viscosity of air. In the same year that he was married, there's Maxwell, Catherine and Toby. The same year he was married, I've said that, when in 1860 Aberdeen merged his two colleges into the one university, Maxwell lost out to the other professor of natural philosophy. Maxwell had already applied for the Edinburgh Chair of Natural Philosophy, which Forbes had left to be Principal of St Andrews. He was up against Tate and Royth, and this time it was Tate that succeeded. Maxwell had beaten Tate to the Marischal College post. Maxwell then applied for the vacant chair at King's College, London, and was successful. For the next 6 very productive and fruitful years, the Maxwells now divided their time between London and Glenlair. The picture is Maxwell in the early 1860s, soon after he became Professor of Physics and Astronomy at King's College, London, at age 29. In his inaugural lecture, he said, "In this class, I hope you will learn not merely results or formulae applicable to cases that may possibly occur in our practice afterwards, but the principles on which those formulae depend, and without which the formulae are mere mental rubbish. I know the tendency of the human mind is to do anything rather than think. But mental labour is not thought, and those who have with labour acquired the habit of application often find it much easier to get up a formula than to master a principle." And he continued with what turned out to be an amazingly prophetic statement. "Last of all, we have the electric and magnetic sciences, which treat of certain phenomena of attraction, heat, light, and chemical action, depending on conditions of matter, of which we have as yet only a partial and provisional knowledge. An immense mass of facts have been collected, and these have been reduced to order and expressed as the results of a number of experimental laws. But the form under which these laws are ultimately to appear, as deduced from central principles, is as yet uncertain. The present generation has no right to complain of the great discoveries already made, as if they left no room for further enterprise. They have only given science a wider boundary. And we have not only to reduce the regions already conquered, but to keep up constant operations on a continually increasing scale." The most important achievements of Maxwell's London years were contained in a series of articles on electromagnetic theory and in which the celebrated Maxwell's equations first appeared, although not in the form that we know it nowadays, as we usually see it nowadays. In January 1865, Maxwell resigned. Mainly it appeared to return to Glenlair to occupy his time with experiments and speculations of a physical kind, with which, as he said, I could not undertake as long as I had public duties. The picture is of Glenlair taken about 1884. The time at Glenlair was not a period of retirement. As well as preparing his great treatise on electricity and magnetism, he produced a book on the theory of heat in which he introduced what was later to be called Maxwell's demon, as well as developing his ideas on the theory of gases. He also continued to be involved with the British Association for the Advancement of Science. Then, 1871, he was asked to go back to Cambridge to set up and direct the first Cavendish Laboratory, or the proposed Cavendish Laboratory of Experimental Physics. And the pictures of Maxwell in his late 40s. I think he's already beginning to look quite strained. Maxwell was not the first to be approached to direct the new laboratory. Thomson had been approached first, and then Helmholtz. Maxwell's emphasis for the laboratory was to achieve measurements of high precision, sometimes to several orders of magnitude better than any previous attempts. In 1877, his health started to fail, and over the following 2 years there were periods when he was in too much pain for work. He died in November 1879 and was buried in Parton Cemetery near Castle Douglas in Galloway with a simple headstone. His mother, then father, then eventually Maxwell, followed by his wife. A simple tomb, worth contrasting with that of Newton's. Let me turn now to some of the more important aspects of his work. There is scarcely a single topic that he touched upon that he did not change almost beyond recognition. And this is by Charles Coulson, the distinguished Charles Coulson, a 20th century successor to Maxwell at King's College, London, also at Oxford. I think he held 3 professorships in 3 different universities in 3 different subjects. 4 in the end.
From mathematics to theoretical chemistry.
Thank you. So I thought that quote is the one to show Maxwell's range, because it is coming from somebody who had a similar kind of range. Maxwell tended to jump between areas of investigation. He was really not a suitable topic for giving a lecture on, actually. If he could have worked in a more consistent way, it would have been very helpful. Which is a lesson for you all. Peter, that is a lesson. And so I want to collect and discuss his work in the areas of Saturn's rings, colour vision, kinetic theory, and then finish with the big one, electromagnetism. It was Maxwell's investigations into the dynamics and stability of Saturn's rings that first gave Maxwell a national reputation, indeed international reputation, and recognition, for example, by Stokes and by Thomson. The question of the ring stability was the subject of the 1855 Adams Prize, named after James Couch Adams, who with Leverrier was given credit for the discovery of Neptune. Here's the announcement of the prize. And let me give it to you and perhaps I'll read out the thing. The problem may be treated as a supposition that the system of rings is exactly or very approximately concentric with Saturn and symmetrically disposed about the plane of his equator. And different hypotheses may be made respecting the physical constituents of the rings. It may be supposed that they are rigid, that they are fluid, that they consist of masses not mutually coherent. And the prize then went on to try to decide upon the various situations. You may notice that one of the setters was William Thomson. Entries for the prize had to be submitted by December 1857. So the three situations: that the rings are solid, that they are fluid, or they're composed of separate individual masses. They're the three possibilities. The problem was difficult, and even the great Laplace, author of the standard work on celestial mechanics, had only obtained partial results in the case when the ring was assumed solid. Laplace had shown that a uniform solid ring would be unstable, but conjectured that a solid ring could be stable if its mass was unevenly distributed. Maxwell first showed that Laplace's intuition was correct, and that a solid ring could not be stable except in a very strange configuration where about 80% of the mass was at one point on the ring and the rest uniformly distributed. And here he's dealing with this case that this loading must not only be very great, but very nicely adjusted, because if it were less than 0.81 or more than 0.83 of the whole, the motion would be unstable. The mode in which such a system would be destroyed would be the collision between the planet and the inside of the ring. So he ruled out, effectively, because of observation, Saturn's rings were not so loaded that they could not be solid. So now we go on to the fluid situation. It turns out that this was to depend critically on how internal wave motions behaved. The gravitational potential set up wave motions in the ring. And Maxwell showed that these waves would cause a fluid ring to break up into separate blobs. Blobs is a technical word. So it would need to consist of separate parts. Next was to consider a ring of a number of different separate parts. Now, the situation of a ring with a large number of objects of different sizes and masses was too difficult, and Maxwell simplified by considering a single ring with identically equally spaced particles. Note the simplification. It's one that he moves away from in his kinetic theory of gases, part of the reason I'm telling you about it. What he did was he showed that such a system would show 4 modes of vibration, but as long as the average density was small enough, it would be stable. And he actually, part of the theme running through the lectures today will be models. Particularly with Julia, where we had the vortex models, and Mark, a lot of the work that Kelvin did clearly was involved with models. And here we have a model that Maxwell had made to illustrate the sort of motion that you could have in a ring with separate particles exhibiting wave motion. And I hope you can read it there, because it brings out that point about models. He said that Maxwell's work on Saturn's rings was one of the most remarkable applications of mathematics that had ever been. Maxwell showed theoretically that the rings must consist of small independent particles, each of which rotated about its mean position in the ring and which are kept apart by the motion of the ring. And then a bit of a dig coming up. I am still at Saturn's rings, he writes to Lewis Campbell. At present, 2 rings of satellites are disturbing one another. I've devised a machine to exhibit the extent of the motions of the satellites in a disturbed ring, and Ramage is making it for the edification of sensible image worshippers. So what he has shown is that you can have rings made up of separate particles going around, being stable as long as the average density isn't too high. Not quite certain whether they're material particles or blobs, but he then uses some observational techniques and says the theory of the rings is further confirmed by recent observations on the inner obscure ring of Saturn. The limb of the planet is seen through the substance of this ring, not refracted, as it would be through a gas or fluid, but in its true position, as would be the case if the light passed through interstices between the separate particles composing the ring. So long before, I think it was Cassini, went to Saturn, Maxwell had shown that the rings were going to consist of lumps of this, that, and the other circulating around. What I couldn't find on the internet was an actual picture from Cassini showing lumps within the rings. There are lots of artist impressions, but I don't want to fob you off with things that aren't the real thing. There we got that. When he considered two concentric rings, he found that stability imposed conditions over the ratio of their radii. Now, the analytic techniques that he showed in this essay owed a great deal to his mathematical studies and background at Cambridge. In the same way, I would suggest that the work I'm going to talk about now on colour owed a great deal to his experimental training at Edinburgh. And the next topic, I want to talk about the kinetic theory, brings together his mathematical and his experimental technique. And the last topic on electromagnetism raises them all to a different plane altogether. While at Edinburgh, both Maxwell and Forbes were interested in colour vision. It had been suggested by Thomas Young in 1800 that there were three sets of colour receptors in the eye. Forbes and Maxwell identified three primary colours as red, green, and blue. They used a wood disc to which three coloured discs could be attached so that different amounts of each colour could be displayed. When the wood disc was spun, these primary colours were in some sense mixed, and the brain perceives a single colour. Persistence of vision, which Maxwell was earlier interested in, seems to be fundamental here. The central area of the wooden disc could contain another colour, and the experiment was to find the proportions of the primary colours that, on spinning the disc, gave the colour in the centre. The important point is that he quantified the effect of combining the three primary colours of red, green, and blue. He represented this geometrically as a colour triangle from his collected works. And some of you may sort of recognise that when you go to do a presentation in PowerPoint, when you go to change the colour of the font or the background or whatever. So this is, worked clearly through to the, because it's core to the present day. The three primary colours, red, green, and blue, are represented by the vertices of the triangle, and each point inside the triangle represents the result in some proportion of red, blue, and green. But as I mentioned, he quantified that, and that's a page out of the paper on colour vision that I mentioned. And you can see some equations in the centre, and what they're doing is they're representing a particular colour in terms of the three primary ones. And when he couldn't get an exact colour, he did various manipulations in order to achieve the result that he wanted. But just like my two previous colleagues, he was asked to give a lecture to the Royal Institution on colour vision, and he wanted to illustrate the lecture and demonstrate that any colour could be made by mixing the three primary colours of red, green, and blue. Well, he didn't have Lord Kelvin's voice. He didn't have film credits to show. What he had was a colour disc that nobody could see from the back of the room. Or he had a colour box, which he had previously designed, but that could only be seen by one person at a time. But there was photography. Perhaps he could use photography to show the phenomenon to such a large audience. And here we see somebody has stolen my line about this being the first colour photograph. The basic techniques of black and white photography were known, and it was possible to project a photograph on a screen for an audience to see. He wanted to see if he could make a colour photograph and project it on a screen for the audience in the same way. That would illustrate that any colour could be made by mixing the three primaries of red, green, and blue. What he would need to do would be to take three photographs of the same object through red, green, and blue filters in turn, and then project them simultaneously on the screen through the same three filters. On the screen you see the result. First colour photograph. It worked, but it shouldn't have. The result could not be duplicated. The problem was that the then available photographic plates were sensitive to light at the blue end of the spectrum, but not very much to light at the red end. Maxwell had been lucky because of a sensitivity of the emulsion to the ultraviolet. Instead of photographing the ribbon under red light, Maxwell was actually photographing it under ultraviolet light. So the mixture of colours which Maxwell obtained were ultraviolet, blue, and blue-green. Not the mixture red, blue, green he believed he had obtained. He'd been lucky, but he made his own luck. Now I want to turn to an area of investigation that shows both his mathematical and experimental abilities. This is the kinetic theory of gases. In April 1859, Maxwell read a paper by Rudolf Clausius about the speed of diffusion of gases. In the kinetic theory of gases, it is proposed that gases consist of a great number of molecules whizzing around. And, for example, their impact with the surface causes pressure, and what we experience as heat is the kinetic energy of their motion. By the mid-19th century, kinetic theory could explain most of the experimentally obtained laws connecting pressure, volume, and temperature. But for the theory to explain, for example, pressure, the molecules would have to move very fast, hundreds of meters a second. But why then do smells travel relatively slowly? Well, I wasn't going to do this until my two previous colleagues, but I brought my bottle of perfume. Calvin Klein. I'm going to spray some. I have to be careful not to spray it into my eye or anybody else's eye. And I have to bring it home. I'll leave that there. Right, it's reached me, but I don't have a great... Okay. If I take the stopper, I've sprayed it, the fragrance will diffuse, will travel relatively slowly throughout the room. Remember, I've just said the molecules are traveling at 700 meters a second. Well, Clausius had suggested that as it goes down the room, you put your hands up. Maybe that way. Good, but not this. Oh, this experiment working. And then it'll go down through the door, down the stairs, to anybody. Thank you. Yes. To anybody that's listening. Clausius had suggested that each molecule you get your value when you come to a BSH Gresham meeting, don't you? Each molecule undergoes an enormous number of collisions and so is continually changing direction. As Maxwell put it in a letter to P.G. Tate, if you go at 17 miles per minute and take a totally new course 1,700 million times a second, where will you be in an hour? There should be a question mark, I know. Also, of course, that is just 1.7 billion. And you realize when they're talking about economics, when they talk about billions, just how large those numbers actually are. So that's what he wrote. Well, Clausius had assumed that all molecules at a given temperature had the same speed. Maxwell, when analysing Saturn's rings, had similarly simplified by assuming identically spaced particles. But his inspiration now was to capture the motion of many particles in a single probabilistic law. It said nothing about an individual molecule, but gave the proportion of molecules that had velocities within a given range. It's absolutely brilliant how quickly he derives this distribution. And it's there. The argument is, if in gas at constant temperature and pressure, that is at equilibrium. Good? Yeah, so it's going as the square root of something. I won't say what. As Robin says, what did you say? That was the exercise, homework? And composed of molecules of the same type. Then let the components of velocity. Now, velocity means it includes what speed you're going at and what direction. We'll talk about speed in a moment, but the velocity includes direction as well as the magnitude, the speed. Let it be x, y, and z along three arbitrarily selected, mutually perpendicular axes. The speed then of any particular molecule will be the square root of x squared plus y squared plus z squared. There's a deliberate mistake in the handout that you can get afterwards where I've given Pythagoras' theorem incorrectly. For a professor of geometry, it's rather humbling. Anyway, so what we've got is we've got the velocity going in 3 different directions, x, y, z. He makes these assumptions, 3 assumptions. First, the number of molecules with velocity in the x direction, velocity x is independent of the number with velocity y and independent of the number with velocity z. So we've got an independence there. Next, that their distributions are the same. Their form is the same. There's no way of distinguishing the x direction, the y direction, the z direction. And finally, that this is a function of the speed only. Only depends the speed with which they're travelling. And as a result, he obtains this functional equation down here. Where's the functional equation? There we are. So the marginal in each of the x, y, and z direction is a function of the speed, the x squared plus y squared plus z squared. And then when you solve this equation, which is relatively straightforward to do, you obtain that the distribution of the velocities in the x direction is a constant times e to an x squared. And what we have then is the now familiar normal-shaped distribution, a bell-shaped curve. So is that one I obtained from the internet. And the proportion of velocities between any 2 velocities, you choose 2 of your particular velocities, that one there and that one over here, is given by the area above them and under the curve. So this is a way of being able to describe the proportion of molecules having velocities in a particular range. Then, as you heat up the gas, as the temperature increases, this curve becomes fatter and flatter. The peak drops down and it spreads out more. As the gas gets hotter, you have a wider range of potential velocities. And it's relatively simple to derive the distribution of the molecular speeds from knowledge of the distribution of the velocities. Oh, and I should also say, you can see there that the average velocity is going to be 0 because it's symmetric about the point 0. Then you can calculate relatively straightforwardly what the distribution of the speeds is going to be, and this is the Maxwell distribution for the speeds of molecules in a gas. And as the temperature increases, the shape goes out towards the right. Now, this was absolutely crucial way of looking things, new way of looking things. It was a result, really, of the first order. It led to a new approach in physics. Previously, statistical methods had been used, but they'd been used for analysing errors in observations. And they'd been used by what we probably now call social scientists. They'd used statistical methods to describe populations. What Maxwell had done was to use statistical methods to describe physical processes. And it was an entirely new approach. It led to statistical mechanics, an enhanced understanding of thermodynamics, and the use of probability in quantum mechanics. And it also helped to confirm that gases consist of fast-moving molecules. This is because Maxwell used it to predict a new law. The new law was that viscosity is independent of pressure. It's quite surprising. The viscosity of a gas is the drag it causes on a body pulled through it, or, if you're letting a pendulum swing in the gas, the damping effect that is caused. And the result is that that's independent of the pressure of the gas. Now, I find this very hard to understand until I saw the reception earlier on. And if you think of the pressure in the gas being the number of people against the bar, the more people you put into the room, it doesn't actually change that pressure against the table because they bump against each other all the time. So that what what's happening in the kinetic theory is that as you increase the pressure, it shortens what's called the mean free path, the average distance that particles travel before they bump into each other. So in a sense, they're screening the pendulum from the effect of the gas. So I thank Robin for his Rhenish wine and macaroons and for the experimental illustration, educational point that it made. I mean, they're all, yeah, right, okay. I think that's the best thing to say about that. Now, Maxwell's work was to provide an inspiration to Ludwig Boltzmann, who spent most of his career developing the subject of statistical mechanics and thermodynamics and putting it on a sound basis. It's very appropriate that the names are now joined in the Maxwell-Boltzmann distribution of molecular energies. And to my final section. The last topic is the one that is most closely associated with his name. He began his researches on electricity and magnetism shortly after graduating in 1854 and continued them until shortly before his death. He was refereeing a paper by G.F. Fitzgerald on the subject. It's a complicated story, and I'll just be able to pick out some key features, which means that I don't want to be asked to put any other feature. The core, as I understand it, is this experiment of Oersted's of electromagnetism. Up to then, you had attraction and repulsion. You had electrostatics, you had like charges repel, unlike charges attract, or perhaps it's the other way around. It's a detail, but the principle's correct. And similarly with magnetic poles, something like that happens. But Oersted's experiment in electromagnetism was very different order. For a start, you had something moving. You had the current moving along this wire. And what happened when you had this magnet set aside is that the magnet, you think of the electric current being in the plane of the paper, what happens is that this pole of the magnet moves out of the paper and that pole moves into the paper. Right? So it's not an attraction towards the current, the electric wire, it's that this magnet is swinging in and out of the paper. Right? Not an attraction, not a repulsion. A different kind of phenomenon altogether. Michael Faraday, viewed this result as crucial in his thinking about electromagnetism. It is core. And his development of ideas about lines of magnetic and electric force. And here we've got a nice picture of Faraday. Again, this idea, I'm sure there's probably smoke rings there, and there's probably a voice box somewhere. And here we have a magnet, piece of paper over it with the iron filings showing what we're going to call Faraday's lines of force going from the North Pole to the South Pole. Okay. Now, Faraday was an important influence on Maxwell, very important influence on Maxwell, as indeed was William Thomson. And Thomson developed a formal connection between the equations of electrostatics and the equations for the flow of heat. Maxwell's first paper on Faraday's lines of force was published from 1855 to 1856 in two parts. And the first part dealt with an analogy between lines of force and streamlines in an incompressible fluid. In the second part, he started the development of the theory of electromagnetism and made extensive use of Stokes' theorem, which we saw earlier when it was set as an exam question. Maxwell's next paper on the physical lines of force attempted to devise a medium filling space that would account for the stresses associated by Faraday with his magnetic lines of force. It concluded with the property that vibrations of this medium have properties identical with light. Now, you think you've seen models. Just you wait. Okay. Look at this array of hexagonal vortices in an incompressible fluid. So we've got vortices, hexagonal vortices. He didn't say they had to be hexagonal. Right, there we are. Okay. Now this is very beautiful. It's an engine of discovery. It's lovely. It actually explains electromagnetism to me, although it's completely bizarre and absolutely nothing to do with it. But let me tell you how he worked his way through it. Normally the pressure is identical in all directions. But if the vortices rotate, centrifugal force would cause it to expand. So here you've got rotating vortices. Cause it to expand along the middle in the plane of the paper and contract along the axis of spin, perpendicular to the paper, in the same way that the Earth's rotation causes it to bulge at the equator and flatten at the poles. So the lines along the spin axis would behave just like Faraday's line of force, because they're contracting. This is perpendicular to the paper now, along the line of spin. Where you have the contraction, you think of these hexagonal arrays stacked one upon the other. So you get this contraction, this tension along the analogy for Faraday's lines of force, and a repulsion sideways, which is exactly the characteristics that Faraday said that he had for his lines of force. But how can you get the electricity coming into it? The spinning vortices represent the magnetism. The electricity is represented by these spheres in between the vortices. And they do two things. They solve the problem that at the moment you have these things rotating. Here we are, here, rotating, and they would rub against each other. But if you put these small spheres in between, they act as idle wheels and gears, and they allow the motion to be transmitted. Right? Let's look at what happens when current flows in the wire AB. So this is a wire AB with the electric particles in it. And as the spheres move along, the current flowing, they're going to set these vortices spinning. Spinning vortices represent the magnetic field. They're going to do something to the next line of electrical particles here, which are then going to cause this to spin, so that what you have is the current is going to cause a magnetic field to move outwards, both upwards here and downwards. But there was one final feature of the model. So it explains the Ørsted result on electromagnetism. But there's one final feature of the model that Maxwell introduced. This was to make the vortex medium elastic. That's why I introduced the paper on elasticity earlier on. Because now the forces between electrically charged bodies could be attributed to potential energy stored in the medium. And this allowed him to develop his great result. An elastic substance is one that can transmit waves. And Maxwell calculated that the velocity of waves in this elastic medium was going to be the ratio of the electromagnetic and the electrostatic unit of electric charge. And that turned out to be the speed of light. As he wrote, we can scarcely avoid the inference that light consists in the transverse undulations of the same medium, which is the cause of electric and magnetic phenomena. In other words, light is propagated as an electromagnetic wave. Well, Maxwell was unhappy, as were many, and indeed all, with this model of whirling cells and rotating spheres, and he wrote, the conception of a particle having its motion connected with that of a vortex by perfect rolling contact may appear somewhat awkward. I do not bring it forward as a mode of connection existing in nature, or even as that which I would willingly assent to as an electrical hypothesis. It is, however, a mode of connection which is mechanically conceivable and easily investigated, and it serves to bring out the actual mechanical connections between the known electromagnetic phenomena, so that I venture to say that anyone who understands the provisional and temporary character of this hypothesis will find himself rather helped than hindered by it in his search after the true interpretation of the phenomena. Well, his fourth paper, A Dynamical Theory of the Electromagnetic Field, published in 1865, resolved the issue as it provided a theoretical framework based on experiment on a few general dynamical principles for the propagation of electromagnetic waves through space without any recourse to vortices or forces between electric particles. And Maxwell wrote again, I think rather sweetly, about this paper. I have also a paper afloat containing an electromagnetic theory of light, which till I am convinced to the contrary, I hold to be great guns. In this paper and in his treatise on electricity and magnetism was 1873, he developed Maxwell's equations, which in modern notation you have on the screen there, where 1873. Right. And of course these equations are exceptionally important both practically and theoretically. But I want to pick out one of the important features that they have, or at least Maxwell's approach has. And it's going back to that quote of Einstein on Maxwell. Since Maxwell's time, physical reality has been thought of as represented by continuous fields and not capable of any mechanical interpretation. This change in the conception of reality is the most profound and the most fruitful that physics has experienced since the time of Newton. And then we come to a sentence I never thought I would say. I think what Einstein might have meant here. I think what Einstein may have meant here was how Maxwell went from a mathematical description of a mechanical model involving vortices, separated by rolling spheres, to the complete abstraction given in his treatise on electricity and magnetism. He stripped away all the imagery of the model until finally all that remained was the mathematics. The mathematics was the model. This approach transformed physics and made possible the development of relativity and quantum theory, and is possibly James Clerk Maxwell's greatest achievement. Thank you.
For all information, please visit www.gresham.ac.uk.